In this segment, what we're going to do is we're going to take a look at one of the four general motion types of fluid, and that will be fluid rotation. And fluid rotation in fluid mechanics is described by a vector omega. So it's defined as being the average angular velocity of any two mutually perpendicular line elements. And the way that we define it, I mentioned it's omega, a vector, and we will have a fluid rotation in the I direction, one in the J direction, and one in the K direction. And the convention that we will use for the sign of it, we will use the right-hand rule, which implies that counterclockwise is positive for the rotation. So when we're looking at fluid rotation, let's draw out a little schematic here. So that might be our original fluid element. Now if it's going through pure rotation, what we can do is that's what our object might look like through pure rotation. So we're going to zoom in on that, and we have our two orthogonal lines that are rotating. We're going to zoom in on that, and we're going to write out some terms, and that will enable us to come up with a derivation for omega, little omega. Okay, so here we have our deformed fluid particle on the right-hand side. And what we have are two different angles. We have a delta alpha and a delta beta. And those will quantify the rate of rotation. And you'll notice I have a delta x and a delta y. What we're going to be looking at is we're going to be looking at the rotation rate of omega OA, that line, and we'll also look at omega OB. So we're going to take these one at a time. That's not a very good omega. Let me erase that. We're going to take these one at a time, and then we're going to average those together, because that's what we said. It's the average angular velocity of any two mutually perpendicular lines. So let's go through and look at this, and we'll come up with the equations that describe the rotational rate of a fluid particle. So to begin with, what we'll say is the v velocity at 0. Let's assume that we could have this rotating fluid particle translating. So we'll give it a translational velocity v naught. So the origin could be moving at v naught. And the velocity at A, looking back at the image here, so we're looking at this point here, A, and we're looking at the v component in the y direction. That would then be equal to whatever that translational velocity is, plus, and I'm going to use a Taylor series expansion here, dv by dx multiplied by delta x. So essentially what we're doing is we're looking at how is the v component of velocity changing as it goes from the origin to this point here, A, and that's how we can express that. We're now going to use that, and we're going to try to figure out the rotational rate of line 0A. So origin is there, A is there. We want to figure out that rotational rate. So what we can do, we can write this out as a limit. And it is going to be the change in alpha divided by the change in t. So if we look back, alpha is just this angle. So we're looking at the change of that angle with respect to time, which is the angular rotation rate. So that's pretty simple, kind of makes sense. But what I'm now going to do is I'm going to substitute for delta alpha, and I'm going to use the small angle approximation in doing this. We keep the limit. And using the small angle approximation, I can say that delta alpha is delta eta divided by delta x, and then I retain the delta t there. And the other thing that I know is that delta eta can be expressed as being the velocity at that location multiplied by delta x. What I've done here is I've taken my Taylor series expansion. That is the differential or the increase in velocity at A with respect to the origin. And then I multiply that by delta t, and that's how far A is going to move in a period of delta t. So I can take this and I can substitute it in to this expression up here. And when I do that, I can re-express my angular rotation and so I have all those, and when you look at this, magically a bunch of stuff starts to cancel, which is great. And what we end up with is just dv by dx. So that is the angular rotation for line 0a. Now I'm going to go through the same sort of logic. Looking back at the diagram, I'm going to look at a line 0 to b. So let's go through the same process. And in this case, I'm going to be looking at the u component of velocity. That should be u at the origin is equal to u0. And then u at b is that origin velocity, whatever the translational velocity might be, multiplied by, and this is basically a Taylor series expansion here. Now what I'm interested in is rotational rate of 0b, so the line to the origin. Again, I'm going to do the limit. And that is just delta beta divided by delta t. And I'm going to make the small angle approximation. So delta beta can be expressed as delta zeta divided by delta y. And then that's all divided by delta t. Now delta zeta, I'm going to get that by knowing the velocity at b. And I can get that from this term here. And notice, here I'm going to introduce a minus sign because it's going to the left. And when I substitute this into my angular rotation expression, I then end up with the following. Again, just like before, a bunch of the terms are going to cancel out. Oops, I just disappeared my delta t. That's gone, that's gone, that's gone, that's gone. What do we end up with? We end up with a minus partial u, partial y. So that becomes the rotational rate of 0b from the origin to point B. Now what we're going to do, remember we said that rotation was the average of the angular rotation of two perpendicular lines. Therefore, omega z is going to be the average of those two rotational rates. And I get that for the rotational rate in the z direction. And I can go through the same sort of argument and rationalization for the other components of rotational rate. And we get this. So we get those, and let's put them all together into our vector. And so we get that describing the rotational rate of a fluid particle. And we can also take advantage of a vector operator, the curl, which is in our review of vectors. And so you can look at that if you want more information. But when we look at the expression that we have for rotational rate, what we find, and if we compare it to the curl of the velocity vector, omega is then just 1/2 del cross v. So that is the expression for the rotational rate of a fluid particle. It is one of the 4 general types of of motion that a fluid can be going through. If you want to go back and see the other types, I'm going to put a return box here. So all you need to do is click on that, and that will take you back, and you can look at others, or you can move on to other segments.